Okay, great. So let's let's begin. So I propose that we consider a problem that is close to the one you have to solve in the project, and in the same way. So I propose that we write a model for solving the shortest path problem, and we will write a model in a mathematical problem using ILP. And naturally, this is not efficient because we know that there exists some algorithm to solve shortest path problem, but we will artificially solve them using ILP. Okay, so it will be longer than solving them with Dijkstra or Bellman or Floyd-Warshall and so on. But this is just an exercise. Okay, and and in the project you have to do the same thing as a matter of fact, because you will solve a max flow problem using ILP, and this is not efficient. We should better use Ford-Fulkerson and or another algorithm to solve max flow problem, but we could do this. Okay, so let's see that. So we will consider an example. So I need to write a graph. So maybe I will take this graph. Just a moment. I will consider one. Okay. Well, okay. Imagine that we will consider this graph, and we will imagine that we want to compute the shortest path from between two vertices. Okay, so and our objective is this one. So let's compute the shortest path between two nodes, two vertices in any graph. Okay, using ILP. Okay, so first we have to write a model to do that, and then we will pass it in Julia, and to have an example of a Julia program for solving a graph problem. Okay, are we okay for the objective?
Sorry, but what is I
Okay.
in your
Um,
programming?
yes. For example, here I would like to find the shortest path from the vertex I to okay, sorry, I in ILP.
Yeah.
Yes, okay. It's integer linear programming. Well, as a matter of fact, this is relevant for the project because for solving max flow problem, we could use either ILP or LP. But in ILP, the variables are integer. Okay, so but it in the max flow problem you have to solve, you just have to consider real variables, so it's not really different, as a matter of fact. Yes, it is different because ILP requires a branch and bound, and LP requires the simplex method. But in the model, we just have to consider integer variables or real variables. So it will be just one line of difference. Okay, so I would like to find the shortest elementary path. So An elementary path is a path that never pass twice by the same vertex. Okay. Otherwise, it would be a bit more complicated. So this, okay. So for what we have to do today, it will be okay. So I is a kind of source, and J is a kind of target. And I want to find the shortest path um, uh, between two vertices. So there will be I and J, these two vertices, using ILP. So the what we could use variables, um, xij, for example, and xij will be set to 1 if the shortest path no. So I would change the name of the source and the target. The source will be S, the target will be T, so that we use the indices ij in the model. Okay, it will be so the source is S and the target is T. So xij will be 1 if the shortest path from S to T uses the edge ij and 0 otherwise. Okay, so if we consider these variables, the model will be quite simple. The data here will be you see the values on the edges. So the data will be, for example, dij, which is the distance um, from I to j. The distance of the edge ij, the weight of the edge ij. Okay, this is known in advance, and we will represent them with a matrix. Okay, so maybe we can write the model, and then we will pass it in Julia. So we have to consider a minimum here. We will minimize z. So z will be the minimal length between s and t, and we have to minimize the sum on all the edges ij. So of the dij xij for ij being an edge. Okay, we will assume that in the data we have a graph G whose set of vertices is X. U, capital U, will be the set of the edges, the directed edges. And here we simply have to compute the minimum on all the edges of the dij xij. Naturally, we simply, for imagine that I don't know what the shortest path is in that case. Well, here we have this one is of length 12. We have better than 12. Well, okay, let's see the solution. I think we have two solutions for. Okay, this is a solution. The solution is 10 with x1, x4, x6, and we have, yes. Do we have another solution? No. Okay.
Can we have these PDFs?
Yes, if you want. Okay.
Yes, please.
but it's in French. I put it in the conversation.
That's not a problem.
Okay, well, sorry, I lost it. Where is it? I drag and dropped it, but I don't know where. Well, just a moment. I will recompute it. Okay. So here I put it in the conversation and the solution as well. Okay, and here they are in the conversation. Okay, so here the shortest path is this one. It will be the final solution. So in the final solution, we will have the variable x14 that will be set to 1, the variable x46 that will be set to 1, and the other xij will be set to 0 for all ij different from not belonging to 1446. I don't know how to represent that for the other edges. Okay, so here we will compute the minimum of this, and the constraints would simply indicate that the variable set to 1 constitute a path from S to T. So the constraint will say that at least one edge outgo x1. So for example, we will say that the sum of all the x s t x j is 1, for j being a successor of s. We will indicate that there will be only one edge incoming the t. So the sum of all the x I t, for I being a predecessor of t, will the sum will be 1. So only one edge arrive at outgoes S. Only one yellow edge outgoes S, and only one edge arrives at T. And we simply have to write a kind of conservation constraint indicating that the sum, if you consider any vertex, for example, for any vertex I in X, but not the source and not the target, well, the sum of the X K I equal the sum on K, for K being a predecessor of I. This equals the sum of the xi k, or I don't know, j, it's of no importance, for j being a successor of I. Do you agree with that? This sum, the two sums can be 0, or the two sum, and this cannot exceed 1. Do you agree? We because I want elementary path. I don't want that too. Well, maybe if we remove this, we would consider non-elementary path. But here I don't. I would like to consider elementary path, so I will add that this sum should be lower than 1. So as a matter of fact, for this model, I will write it in 2 constraints. So I will simply write that the sum of everything that arrives at I, for example, is lower than 1 for all I. Okay. And that way, I think everything is okay. And you see that this model is very close to the model of the max flow problem, as a matter of fact. That's why I wanted to consider it today, for all ij being an edge. Okay, so now I propose that we pass this model in Julia. Is there are there some question about this model, or is it clear? See,
I have a question.
yes,
Because the path you choose is x1, x4, x6,
yes.
and the n the flow to t is 1, so you make it less than 1.
Uh, in this problem, this is not the problem of the project. This is a problem that is close to the problem of the project, and there is no flow. As a matter of fact, we simply have to compute a shortest path here. You see, as a matter of fact, we should use Dijkstra algorithm. You see, for solving this problem. But here, we will use linear programming, more precisely integer linear programming, to solve this problem. So we simply have to come. Do you agree that the shortest path is this one?
Yes, yes, it's
Okay, and we simply have to select the edges that will constitute this shortest path.
yes,
Yes, yeah, okay. In the project, the models that you will have to implement naturally will not be this one, but it will be very close to this one because it's the model of the max flow. No, I did not copy it, but you have it in the slides. Yes. Yeah, so I just say that because you talked about flow and there is no flow here. We simply have to select some edges.
yes,
Yes, okay. So this is our model now, and we would like to transcript this model in Julia, and then to make Julia solve it. And we should find 10, the solution. If we find 10 in in 1 hour, we will be happy. Okay, because 10 will be 9 plus 1.
yes,
Okay, okay. But what you will have to do will be very similar because in the in the project you will have to compute the max flow between S and T. Okay, so to write a method computing the max flow between S and T, here we simply compute the shortest path between S and T.
okay,
Well, let's do that. So I take a blank page. I will keep the model here. So first we have to we have uh, to write. I will take another page. Okay. We have to write the matrix of this graph. So this graph will be the graph G. Okay. So in Julia it will be an array of a matrix, as a matter of fact. So it will be a 6 times 6 matrix. So I will write the adjacency matrix of this graph first, and then the matrix of the distances. I will consider two different matrix, one for the edges and the other for the distances. Okay, not to so the adjacency matrix will be a binary matrix with 0 and 1, and the matrix of the distances will be an integer matrix with the distances, okay, the weights. Okay, so here in the first x1, okay, 1, 1, 1. It won't be. I just want to copy that. How many? 6 and 1, 2, 3, 4, 5, this. Okay. So to declare a matrix of 6 times 6, Julia, we can do something like that. Okay. I think it will be okay. I will try in Julia just to create this to verify the syntax. So Control C and right click in Julia to copy. Well, it is. Well, there is no semicolon. Begins well. So what is? I did that several times. So what's the problem? Ah, maybe it's a semicolon here. I'm not sure. Well, this is the syntax of the graph I send you in the email. Well, okay, now it's okay. Okay, so here this is a 6 times 6 matrix of int 64, and we will represent the graph. So x1 is linked to x2, to x3, and to x4. Okay, so this represents the edges. X2 is linked to x5, and that's all. X3 is linked to x2 and to x6. Okay, and that's all. X4 is linked to x3. Yes, x5 is linked to x6 and to x3. Okay, and that's all. And x6 to no one. Maybe now the distances. Okay, so from x1 to x2, it's 2. This is the distances. From x2 to x3, no, it's x1. x1 to x3, it's 6. x1 to x4 is 9. Okay, then this one, x2 to x5, it's 1. It's okay. x3 to x2 is 1. Okay. To x6, 6. That's all. From x4, it is 1. Okay. x5, it is 2 and 9. Okay, and that's all. And 1, 2, 3, 4, 5, 6, 7, 8, 9. No, one edge is missing. Okay, there are 10 edges in the graph, and here we have only 9 ones. Do you see which edge is missing?
x5 to x3.
Thank you.
We have done it.
No,
It's
yes.
existing, yes.
Okay, it's x4 to x6. x4 to x6. Okay. and it is 1. Okay, so now we have the graph and we have the weight. So we will use them in our program in Julia. Okay, so let's so this now will be the the representation in the program of the graph, and we will write a Julia file. So I will put it in my desktop, for example, in okay, example Julia, okay, and I will call the file shortest path problem spp .jl. So this program will contain the Julia program for solving the shortest path problem. Okay, first I will declare, I will indicate that I will use CBC and JuMP, or JuMP and CBC. Okay, and then I will put these two matrices somewhere in the program here, for example. Okay, I will now compile this program in Julia. I will include it in Julia. So when you are in Julia, for example, this file is in my desktop somewhere. We have here I have the path of the file, so I need to go there in this directory to be able to compile this file. So let's do that. So I wrote okay. So here I have the path corresponding to my computer, but you may find it. For example, you have to find the correct path. If you don't know how to do that, I can show you. But here you simply have to find the path where you will put the files, and then to go there with the command cd. So here I want to go in my desktop, so I want to go in this directory. So now I am on my desktop, and now I go in the folder named example Julia. You can complete the path with the tabulation touch on the keyboard. If you begin writing the name of the folder and then tabulation, it will be completed automatically. Okay, so now pwd, I check that I am in the correct folder. Okay, and I can now execute the file spp.jl. So I will do that. Include spp.jl. And this will simply, okay, you see that here we have the last instruction, sorry. So now the matrix G and D are set. Okay. So a Julia program consists of several definition of functions, and then at the end you call a function. So here we will write a function SPP for shortest path problem, and at the end, okay, we'll complete it, and at the end of the program we will call this function SPP. Okay, so the structure of the program will be this one. Naturally, we could launch this function several times. Okay, if we want to find the shortest path from 1 to 6, then from 2 to 3, etc. Okay, we will try to do that. Okay, so let's do that. So the function SPP here will have several parameters, and it will have at least 4 parameters: the graph itself, the matrix of the distances, the source, and the target. Okay, so when you declare a function in Julia, when you indicate for indicating the parameters, you have to give the name of the parameter, G, for example, and then 2 semicolons like that, and then the type of the parameter. So G is a matrix of here we have I have the type, so I will copy this type. Okay, so G is a matrix of ints 64, D as well. Okay, S will be an int. So int is always int 64. I think simply int is okay, but nt is an int 64. So I will compile just to be sure that everything is okay. So I'll at the end I launch GD 1.6 because I want to compute the shortest path in the graph G with the distances D from vertex 1 to vertex 6. So I here in my Julia window, I include spp.gl. Okay, and for the moment it works. So I will maybe put this file in the conversation so that you have the skeleton of the program. Where is it? In my desktop. Okay, spp.jl. Okay, I copy the file for the moment, but it won't be synchronized. Okay, I will put it several times so that you could have this example. So this is the structure of the program, and now we will write the program, the mathematical model by itself. So I will need an example because I'm so I will look for an example of Julia program. Yes, this one I think would be okay. This is a traveling salesman problem. Okay, so just a moment. I would like to have the 2 examples. Here we are. Okay, so this is our problem, our example, SPP, and this is an example of the syntax so we first have to declare the model. So M will be the model. Here we use the solver CBC, not Cplex. So Cplex is much more efficient than CBC, but it is not free. It is free for the students and the teachers, but not free in the enterprises. And it is more difficult to install than CBC, so we will use CBC. Then we will, so now the model exists. M can be M is the problem itself, if you want. This P, capital P. So the problem P is the model M in Julia. Okay, so now we declare the variables. So here we have okay, n square variables. So here we need to know the number of vertices. Okay, so to have the number of vertices, okay, G exists. I think we have the function size of G1. Okay, size of G1 is the first dimension of the matrix. So it is the number of lines, I think. And size of G2 will be the number of columns. Okay, so here, this is the number of vertices. And we need to have the number of vertices in the model. It will be much more simple if we know it. So I will call n the size of G1. Okay, this is the number of nodes. The comments begin with a sharp. Okay. Well, maybe we need. Maybe we will need all the edges, but I don't know. I don't think we will try to make it as we can. So let's begin with the definition of the variables. So we have to write what is called a macro in Julia. This is so variable here is a special statement in Julia that that is not in Julia. This is specific to the JuMP library, as a matter of fact. And well, the syntax, I don't know the syntax. Okay, we have to, well, it is exactly like that. You see, we will, the variable will be attached to the model M. It will be the variable xij for I in the range 1 to n and j in the range 1 to n. And these variables are binary. So, okay, I simply copy that because this is how we can copy this. Okay, so now the variable xij exists and they are binary. In the max flow problems, the variables are real and non-negative. So if you want to declare real variables, I think you just have to replace comma binary with something like that. No comma and non-negative, like that. I try this because I'm not sure of the syntax, but I think it's like that. Oh, well, I lost. Well, I lost my my window. Oh. Okay. Okay. And include spp.jl. Here I include the file just to check the syntax. If this syntax is okay. It seems to be okay. You see, it takes some time because here the library JuMP and CBC are loaded, and this requires some time. Okay, but just for the first time, if I include once again the file, it will be immediate. Okay. Okay, so here we have our variables now, but so if you have to solve a max flow problem, the syntax will be this one. Yes, Thierry.
Yes, sir. I just want to ask about the second matrix. In our
Yes,
case, we don't have capacities. The capacities are equal to 1. Do we need a second matrix for that?
I don't think so.
Okay.
Yes, you can use only one matrix that will so you will have you can represent yes, the capacities is the matrix of the capacity is exactly the matrix of the adjacency matrix. Yes, that's right.
Okay.
Mm.
Okay. Thank you.
And here, as a matter of fact, we could use only one matrix, the matrix D, but I prefer to use two matrices. I think it will be more simple in writing the constraints, but I'm not sure of that. Yes, Ali.
What the CBC dot optimizer do? The model.
Okay, we will write the model, and then once we have write the model, we will at one time launch the optimization, launch the branch and bond algorithm. And here you see for executing the branch and bond, this will be done with the function optimize of M. Well, here, if you use CBC, it will be the branch and bond of CBC. If you use Cplex, it will be the branch and bond of Cplex. Okay, but there is not only one way to implement a branch and bond, and you can so the branch and bond of Cplex is much more better than the branch and bond of CBC. It is about 2 times faster. If you if you make some experiments, you will see that. So CBC is the solver. You see here, we simply write the model. So the syntax of the model is the syntax of JuMP, and CBC is the engine, if you prefer, that will optimize. It is a solver. So JuMP is a mathematical language, if you prefer, and the CBC is the solver. It is the program that will solve the model.
Okay, thank you.
Okay, and you see if we change the solver here, for example, in that example, you see I use Cplex, and but the syntax is exactly the same for writing the model if you use Cplex or CBC, but you just have to indicate at the beginning of the function that the solver you use will be Cplex or CBC or GLPK or Gurobi. There exist many different solvers in the real life. Yes, but the best one is Cplex for LP or ILP, and but it is commercial. It is not free. CBC is absolutely free, so that's why we use it. Okay, so we have our variables now, but in that case, the variables are binary, so I will indicate bin here. Now the constraint. So you can add the constraints, you can add a group of constraints. So this one, but here you see the difficulty in this constraint is that we have to write this constraint. Well, it's not really easy because of the sum. Well, let's try to do that. Just a moment. How did I do that in here? Okay. Well, we will try to do that. But, okay. Okay, so the constraint now. The first one, I would like to find okay. So a macro constraint. We attach this constraint to the model M, and only one edge out goes the source S. So we have here this I will name this constraint C1, and this constraint is a sum equals to 1. So it will be a sum equals to 1. Okay, this is the structure of the constraint. And we have a sum of the xij, no, xsj. Okay, but we have to precise here that we sum on j. So for j in, okay, we could prepare here. You see a set corresponding to the sorry, the successors of S. Sorry, I am thinking about it meanwhile. Here I will do it like that. We will sum the xsj for j from 1 to n only if j is a successor of S. So I think the syntax is this one. If g of sj equals 1. I'm not sure if the correct syntax is if or if it is a semicolon. So we will try this. Well, it is okay. It is okay. And here, if I want to be sure that everything is okay, I will display the model. So I will print M, the model M, just to be sure that my constraint is okay. Oh, well, I did not save the file, so maybe it's absolutely not okay. Okay, well, I did not save the file. Okay. There is a feasibility problem. Oh, that's perfect. I am quite surprised about it, but you see, the constraint seems to be absolutely okay, because the first constraint here is x12 plus x13 plus x14, x12 plus x13 plus x14 equals 1. That indicates that among the edges 1, 2, 1, 3, and 1, 4, we will only select one edge, because we want to find an elementary path. So we will exit x1. Okay, so the syntax is this one. If you have a condition like that, you see, if you have a condition on the indices here, it will be exactly something like that. We will sum the xsj for j in 1 to n, and we restrict j with an if statement like that. If a condition, and this condition can be complicated. It can be a Boolean expression. You see? If you understand that, you can do anything in Julia. What you can do is to add constraints depending on an if statement. You can write something like that. You see, if condition, well, a condition it would be a Boolean condition. You can add a constraint. Okay, this is this is possible as well in Julia. So that's why it is quite easy to write model in Julia. You can put the condition outside or inside. You see, but here we were. It was necessary to put the condition inside because it's a condition on the sum. You see, not on the quantifiers here. So let's continue. So I remove this. We'll put it as a comment. Okay, now the condition on T, but it's exactly the same thing. We will write a constraint linked to the model M. It will be the constraint C2. And this is a sum. A sum equals to 1. And what do we sum? We sum the xit. Okay. So t is fixed. Okay. T is the parameter of the function. So and we sum the xit for I ranging from 1 to n, and a condition on I. I must be a predecessor of T. So if G of what? So I must be a predecessor of T. So IT must be equals to 1. I think it's okay now. We check it. So I launch the program, and the model will be printed. Okay, for it seems to be okay. Okay, so here we have the predecessor of T, x3, 6 plus x4, 6 plus x5, 6. Okay, that's okay. So this will indicate that among the edges arriving at x6, we select only one vertex. Sorry, only one edge. Okay, let's continue. Now this set of constraints. So you see here, we have a set of constraints because we have one constraint for each vertex, different from the source and the target. So let's do that. So we have a constraint statement. We link it to the model M. And here, okay, I will name this constraint C3. I don't know, it's a kind of continuity constraint. Okay. And we have a set of constraints. So to indicate that you have a set of constraints, you indicate it like that between square brackets. And the constraint will be written here. But here, to indicate that you have a set of constraints, you indicate here. You will have a constraint C3 for I in 1 to n. Sorry, I just have to check the syntax. Yes. Oh, well, I don't know. Okay, I don't know because here I don't have any example of this. Okay, so what I would like to write is something like that. If I is different from S and I is different from T, but maybe that's not the correct syntax. We will check this. Okay. And we have to write this You see, if this is not correct, I'm not sure of this syntax. If this is not correct, we will write something like that. We will write a constraint with a loop. Okay, and I am certain that we can do that. Okay. Obviously, here we could write for I in 2 to n minus 1. Okay, but I would like to test this syntax with you. So, because the source is not always the vertex 1 and the target is not always the vertex n. this sum. So this is a sum. I will write it there. This sum equals another sum. This is what we want to write. The sum of the xki. So we sum the xki for, so I is fixed, okay, because it is in the quantifier. For k being a predecessor of I, so for k being a vertex of k is between 1 and n, and k must be a predecessor of I. So we can write that if g ki exists. So if gki equals 1. Okay, this sum must be equal to, okay, I write it there, the sum of the xij. Okay, for j in 1 to n, if j is the successor of I. So if j of ij equals 1. Okay, we check the syntax. I am absolutely not sure of this part of the. So let's try this. I did not save the file, so Control S to save the file, and we try. Okay, right. There's a problem. So here maybe to check this. I will first try this to n-1, but I want to avoid this. Okay, but let's see if the rest is correct. Okay, it seems to be correct here. You see, we have several constraints C3 of 2, 3, 4, 5. So C3 of 2 is a continuity in 2, in vertex 2. And we say that, where is the graph? For example, in vertex 2, so we write x12 plus x32, x12 plus x32 equals x25. Okay, that's okay. Okay, so the rest of the syntax is okay. So we have the continuity here. We just have to find how to express this. I am quite sure it is possible. Maybe it's a semicolon like that. No, I don't know how to. How we can say that in English? It's not a semicolon. It's 2 points. Well, let's try this syntax. It's not like that. Maybe it's if, and maybe the problem is there. Ah, well, maybe it requires an end. No. Let me check. Otherwise, we will do something else. No. Okay. No. Okay. It's a semicolon. Okay. Okay. It's what I was searching for. Oh, right. Okay. So you will have with this example. So it is not if, it is a semicolon. You see, if you are in the quantifier, so if I is different from S and I is different from T. You see, it's a bit difficult because when you describe a sum, the condition is an if, but when you describe a set of constraints, the condition is a semicolon like that. So let's verify this. Yes, it seems to be okay. Okay, for the constraint for the vertex 2 is now okay, for the vertex 3 is okay. And okay, so we have the continuity constraints now. We can continue. This one, well, this syntax is, this constraint is quite simple for us now. So we have a constraint attached to the model M. I will call this constraint C4. We have a quantifier, so we have a set of constraints. We indicate it in square brackets. And we have a constraint for all I in the set of vertices, so from 1 to n. And we have a condition on n, on I, sorry, I should not be the source of the target. So in this definition of a set of constraints, the condition is a semicolon like that, and we have the same thing. So I is different from the source and I is different from the target. And now the condition is that the sum of the variables outgoing outgoing I, no, not outgoing I, arriving at I must be lower than 1. Okay, and that's all. And now we, okay, I check that by compiling again. Okay, it seems to be okay. We have all the constraints now. We simply have to indicate the objective function. So for indicating the objective function, we have an objective statement like that. Linked to the model M. Here we want to minimize something. It's max for maximizing, naturally. And we simply have to minimize the sum. So the sum of the dij times xij. So this is what we sum. We sum the dij xij, and we will precise the range of I and j. So for I in 1 to n, j in 1 to n, and we have a condition on I and j. So in the sum, the condition is if the edge ij exists. So if g ij exists, so equals 1. I think it's okay. So we will check our model now. No, something is missing comma or bracket in argument list. Oh yes, this is the end of the sum, and this is the end of the objective statement. Okay, and here we have our model that is complete. So we can verify that everything is okay. Minimize x2, x12, 2x12 plus 6 is 13. Okay, that's okay. For example, 2x52, 2x53, sorry. Okay, that's okay. So now I do not display the model again because it is correct. We see that the model is correct. We simply have to now launch the solver. So optimize. I don't know how it is in English. Exclamation mark, something like that. M. Okay, this mark simply indicates that the first parameter will be modified, because here we will set a value to the variables attached to the model. So that's why this mark here is necessary. And so once we have done that, let's a branch and bond will be launched. Okay, so here we have the branch and bond. You see that the branch and bond. Well, we have many informations. We can discard this information with a set silent mode like that. If you do not want to have this information, you can do something like that, set silent of M. And if you say set silent, well, you won't have any information during the branch. Oh yes, you have, but you have less information. Okay, maybe it works with simplex and not with CBC, but that's of no importance. And then now we will display the solution. So let's display the solution. So first, the shortest path, the length of the shortest path. So this is so the length of the shortest path, elementary shortest path from S to T is, and we hope that it is 10. So the objective value can be found in, I will take it. It is something like, here we are, objective value of M. See, we have this function of the JuMP library, so objective value of M. So let's do that. And if we have 10, we are happy. Okay, we have 10. So the length of the shortest path from 1 to 6 is 10, and this is 9 plus 1, and that's okay. Maybe we can display the shortest path. So to display the shortest path, we can simply display the edges of the shortest path. Maybe it won't be in the correct order, but that's of no importance. So println edges of the shortest path. So we will now display the value of the xij. So for I ranging from 1 to n, this is in Julia. This is a loop in Julia. And the loop in Julia is like that. For I in range, end. And here we have a nested loop. So for j in 1 to n, end. And here, inside this loop, we will display the value of xij. Maybe we can simply display the xij that are equal to 1. So if I would like to write something like that, if xij equals 1, then I will display ij. But this cannot be done. If you want to get the value of the variable xij, you must call a JuMP function, and this function is, don't remember it. Well, I need to find another. It's a value JuMP.value, I think, something like that. Sorry, I will take another example. GSDP, exo5. No, another one. Oh yes, this will be okay. Yes, it is JuMP.value of JuMP. The function JuMP.value. Okay. So JuMP that value of x, and this function returns a floating variable, a float or a double, but it's okay if you write something like that. So it will be okay. So the if statement is if condition, well, then some instruction finishing with an end, and here we will display the edge ij. So the edge I, comma j. Okay, and that's all. And at the end, we will go to the line with a println statement. So now you see, we can. Okay, I did not save the file. Okay, so the edges of the shortest path are edge 1, 4, and then edge 4, 6, and we have and we are done. Now, for example, if I want to compute the shortest path, all the shortest path here, once the function is okay. So here we have the shortest path from 1 to 6. If I want all the shortest path, I can write something like that. So for S in 1 to size of G. Okay, this is the number of vertices. For T in 1, okay, and okay. Here we can what we can do is to launch SPP of G, D, S, T. Well, maybe we will have some problems because you see there is no path, for example, from 6 to any vertex. So we will have infeasibility well, the minimum should be plus infinity. I don't know what will happen if there is no path from 6 to 1. Okay, let's try that. In your oh well, you will have this problem in the project maybe. I don't know. I don't think so because the graph is always strongly connected. So the graph I propose to you are all strongly connected. So you won't have this problem. Okay. So here we have some problems for some pair of vertices. You see, it is okay for so from 1 to 6 it is 10. No, sorry. No, okay. Here we have the last. So from 1 to oh no, it is this one. The last call is this one. So from 1 to 6 it is 10 and the path is 1, 4, 4, 6. And here we have a problem. I don't know why it began with 1 to 6 because T it should be from 1 to 1. Well, maybe we can do that only if T is different from S. Okay. Well, okay, here we are. So well, generally that's okay because so from 1 to 6 that's okay. From 1 to 2. Oh yes, the first call is from 1 to 6. Okay, because we launched SPP from 1 to 6. Then we launch SPP from 1 to 2, and the answer is 2, and with the edge 1, 2. So from 1 to 2, it is 2 with the edge 1, 2. Then from 1 to 3. From 1 to 3, it is 5 with the edge 1, 2, 2, 5, 5, 3. That's okay. And then from 1 to 4, it will be okay. 1 to 4, it is okay, and it is directly 1, 4 with a length of 9. Then from 1 to 5, it will be okay. It is 3 with 1, 2 to 5. Then from 1 to 6, we know that it is okay, and this is the path in yellow. And the next problem is from 2 to 1, because there is no path from 2 to 1. Okay, so here the program crashed because the maybe you see there is a problem because we say that we select only one edge arriving at 1, for example, the first constraint, and there is no edge, so the program is infeasible. So it must be, what we can do here is to test the status of the problem, and we can do that by writing something like that. If we here, okay, we test the status of the termination, and we have an optimal solution if the status equals the constant MOI dot optimal. So this will be true if CBC found an optimal solution, and if the polyhedron was not empty, if there was one solution. So if is optimal is true, we will print something like we found an optimal solution. Otherwise, we can say that the problem could not be solved, for example, and we will put this here. Well, I don't think you will have this problem once again in the project, because all the graphs that I gave to you were strongly connected. So I think you won't have this problem in the project. Well, okay, that solves the problem now. When there is no path from the source to the target, we simply write the problem could not be solved. That indicates that there is no path from the source to the target. Well, I give you this file SPP, and well, now the problem is to adapt it to the project, but the project is quite similar to this problem. It's not the same, but it is similar. Okay, so I hope you have it.
Sorry, but I don't know how to get these files.
Sorry, you don't know how to
Got these files that you are.
well, in the conversation here, I think you can simply click, or you have download or télécharger.
No,
Télécharger.
they are not appearing. all of these.
Really? Oh, well, I can put it. Do you have the SharePoint? I can put it in the SharePoint as well. Oh, okay, I understand. Yes, maybe you don't see the conversation. If you are not logged in with an address in lecnam.net, you don't see the conversation. Okay, so I will put it in the SharePoint.
Okay.
Do you still have the SharePoint? Yes. Okay.
I am logged in.
Okay, I will
I'm
give
logged
it
in with
to
a
you.
CNAM. I am logged in with a CNAM email, but I still can't find it.
Okay, just a moment. I think for me it's this one, so I will put it there. Okay, so I think it's this one. Yes, the time is okay. No, the time is not okay at all. It was 1 hour ago, so I will take the good one. Yes, the time is okay here, and I put it there in the SharePoint, and I think you can get it this way. So if you go to the page of the course, so I think it's this one / tilde k.sys / or. Okay, you go to this page, then you have a link through the course material here for me, and if you follow this link, you should find. Okay, maybe it's not synchronized, so I refresh. We should wait for the files to be synchronized. I think I have a notification when it is synchronized. Yes, it's not, you see, it's not green. So maybe I can force the synchronization. And I'm not sure. It is there for me. Yes. Okay.
Maybe it's because the file is still open.
Oh, you're right. You're right. I will close it. And it is not. Well, I moved it. Okay. Yes, I want to. Just a moment. That's okay. I close the file. And I don't know how to force the synchronization. Well, maybe I can send it to you by email. It would be faster. Well, okay. Where is it? Okay. Okay. I will send it by email. And so I am looking for your addresses. Um, where are you? Okay, you are here. Okay, I'm looking for an email with all your address, and that would be okay. Just a moment. Okay, here. Oh yes, now it is synchronized. Do you want me to send it by email, or is it okay? You see, it is synchronized with all the other course material.
We got notification. Yeah.
You get it?
Yeah.
Yes, great. Okay. Well, so we finish here, or do you have other other question? You see the link between what we did and the project? Well, as a matter of fact, for the project, you will have to. Sorry, I need the file. You will have to compute the max flow for. You will have to compute the max flow for not every pair of source and target. It will work if you do that, as a matter of fact, but you simply have to compute n max flow between the vertex I and the vertex I plus 1. So it will, but if you have the same structure, it will be okay. And here you do not have to compute the shortest path problem, but you have to compute the max flow. And at the end, you have to take the minimal value. So that's quite similar with what we did here, as a matter of fact. Okay, so well, I wish you good luck. I received one project, so thank you. I will answer you. But if you have any other question, do not hesitate. Okay, when you try. Okay, so
Thank
so
you.
see,
Thank you.
you're welcome, and see you later. So do not hesitate to ask question. Okay, I stop the recording.